Well, good evening, everyone. I'm Susan L., Vice President and Executive Director of the Foundation for Barnes-Jewish Hospital. Welcome to all of you who are here in person, and thank you for joining us for our Leading Edge Medicine, and welcome to all of you who are joining us virtually. So we are recording and streaming. Our Leading Edge Medicine series is an exclusive opportunity to hear firsthand about the incredible innovations and discoveries happening right here in St. Louis. The Foundation's generous donors play a significant role in these medical advances. So on behalf of our families, friends, and community, thank you for improving healthcare for all of us. Tonight, you're going to hear how your gifts brought a revolutionary idea to life. Your seed funding for out-of-the-box thinking sparked the development of an implantable device that has potential to replace the need for insulin injections for the 10 million Americans with type 1 diabetes. How's that for life-changing impact, right? Transplant pilot project grants funded by donors to the foundation helped Dr. Mohamed Zayed, our speaker tonight, get his idea off the ground and develop and test multiple prototypes of the implantable device. The foundation grant also triggered additional outside grants, including one from Mid-America Transplant, and I'm very pleased to welcome Mid-America Transplant's Chief Medical Officer, who's here with us, and a board member, Dr. Will Chapman. They are Chief Medical Officer Gary Markland, Dr. Gary Markland, welcome. Truly longtime partners of Barnes-Jewish Hospital and the Foundation. Thank you so much for your continued partnership and for being here tonight. We appreciate it. We're grateful for our visionary donors who make vital progress like this possible and advance our mission to enrich lives, save lives, improve community health, and transform healthcare. After the presentation, we will hear from Foundation Board Member, Philanthropy Committee Chair Tom Cohn. He'll finish out the meeting here this evening. And first, we would like to recognize our Foundation board members who are here tonight. They are wearing the gray and silver name tags. If you see them, be sure and say hello when we're in our reception after the program. I think we have Tom, Sandy, Isla, and Keith. So be sure to give greetings. And also our foundation team members are wearing the silver name tag, so be sure to say hello to them. And a special thank you to Emma Bayless, who is our special events, and for our special events team for putting this night together. Isn't it wonderful? We've had such a wonderful turnout. So now it is my honor to introduce Dr. Mohamed Zayed, and I have a few things to share with you about him. He's a renowned vascular surgeon who treats patients with cardiovascular disease. Research is such an important part of Zayed's work, Dr. Zayed's work. He is the Director of Vascular Surgery Research and the Director of Multidisciplinary Cardiovascular Research Innovation in Surgery and Engineering Center, known as CVICE. In addition, Dr. Zayed is the primary investigator of multiple research grants evaluating critical topics in vascular disease and novel technology development. In his various roles as physician, surgeon, educator, research scientist, and academic entrepreneur, he has led and worked with diverse teams in science, medicine, engineering, business, and entrepreneurship. Over the last 5 years, Dr. Zayed has filed more than 40 patent applications. He's received 4 patents and has co-founded 3 startup biomedical companies. Not one to rest on his laurels, however, this MD, PhD also completed an MBA at the Olin Business School at Washington University just in 2023. This academic pursuit led him to receive the prestigious C. William Emery Award from Washington University. This is awarded to the graduating executive MBA student who best exemplifies the qualities of scholarship, character, and leadership. Congratulations, Dr. Zayed. Dr. Zayed also received multiple other honors and awards throughout his career. In 2023, he was also recognized as the Distinguished Fellow of the Society for Vascular Surgery. In addition, he received the Washington University Honors in Innovation and Entrepreneurship. Foreshadowing his groundbreaking work on the implantable artificial pancreas device, Dr. Zayed won the Academy of Science of St. Louis Innovation Award in 2020. This award recognizes a scientist or engineer age 40 or under who has demonstrated exceptional potential for future accomplishments in science, engineering, or technology. Considering the depth of Dr. Zayed's science and engineering expertise, combined with the skills as a vascular surgeon, it's so easy to understand how this brilliant physician scientist crossed over into the transplant world to develop an implanted artificial pancreas device. The unique intersection of disciplines behind the creation of the device reflects the collaborative culture at Washington University and Barnes Jewish Hospital. The new Plaza West Tower, which you might have seen rising above Kings Highway, will open in 2025 and foster more of this pioneering cross-discipline work that Dr. Zayed and his colleagues are doing in heart disease to bridge related areas such as diabetes, cardio-oncology, and cardio-obstetrics. Dr. Zayed's inquisitive mind, entrepreneurial spirit, and his expertise as a vascular surgeon make him the ideal person to look at a problem differently, partner with other experts, and come up with a solution. As a vascular surgeon, Dr. Zayed frequently inserts grafts so patients can receive dialysis. This procedure sparked the idea to use the graft concept for other purposes. So Dr. Zayed focused on developing an implanted device that could act as an artificial pancreas in patients. Seed funding through the Foundation's Transplant Pilot Project grants fueled his innovative idea, and it allowed Dr. Zayed and his team to partner with Washington University McKelvey School of Engineering to construct the prototype of this revolutionary implanted device, which is now called NewPanc. Dr. Zayed is going to tell you much more about this incredible breakthrough. NewPanc could be implanted to regulate blood sugar so patients with diabetes wouldn't need insulin injections. This, in turn, could reduce complications associated with diabetes. NewPanc has potential to treat other diseases as well, and clinical trials are on the horizon. This is an exciting achievement, such an exciting achievement, and it's all possible because of generous donor support. So thank you on behalf of the Foundation, the hospital, and all the patients and families whose lives you will improve. I can't wait to learn more about this game-changing NewPanc device from Dr. Zayed himself. I'm sure you're ready to hear from him yourself. After his presentation, you'll have an opportunity to ask questions and learn more. So now please welcome Dr. Mohamed Zayed. Dr. Zayed. Thank you.
Wonderful. Thank you so much for that wonderful introduction, Susan. And thank you so much for being here. What a wonderful venue and a wonderful event. And it's so nice to see that there's so many people here in attendance, so many familiar faces. And actually, before I start, I wanted to see if there are any patients in the room that would like to stand and be recognized. You are the reason we're here. And truly, that is the reason we're all here, right? We're all here to make patient lives better, to find ways that we can improve health, reduce morbidity, improve outcomes, and do it all in a way that's gonna be impactful long-term on society, right? And so today, I'm gonna be exploring with you the creativity that's involved in this, right? And when I say creativity in surgery, we're not turning the operating room theater into a musical orchestra. That's not what we mean by creativity. It's not that we're taking our scalpels and turning them into musical instruments, but what we're rather doing is in the buzz of things, when there's a multitude of things happening and surgeons have to make a decision or have to make an impactful way to improve the patient, the patients that entrusted their surgeons with their lives, there has to be a sense of creativity in terms of being able to find a lasting solution that will help these patients heal. And so what I'd like to do is I'd like to first explore with you kind of my background in this, and then we'll take some lessons maybe perhaps together about how surgeons have been approaching this and how we hope to continue to approach this in the future. So as disclosures, as part of the solution to try to be able to take discoveries from my clinical practice, from my research center, and from the experiences that I gather from my patients, I've had to start up companies to be able to try to translate these discoveries into the clinical arena. And so, as you can see, there's 3 companies here that I've listed that I've started myself, along with executive talent here in the St. Louis community and outside. And these companies serve to be able to help translate these discoveries out to the public. I also want to disclose to you that I'm a big-time soccer fan. And there's actually one soccer player I know in the audience, right? So Jim is a prior goalie, and he actually wrote a book about his experience as both a patient and a goalie. And as part of my background as a soccer referee, a US soccer referee, one thing that I learned as a referee is the importance of resilience. Nobody likes the referee, right? And that's okay, right? You have to deal with critics, right? People that don't agree with your decision, people that want to challenge your opinion. And at the same time, you have to be ready to make split-second decisions. You have to be ready to be able to pivot and adjust. And you have to be conscious of where things are going and anticipate things ahead of time. And I've kept these lessons with me in medicine and in surgery. I keep this picture in my office for a couple reasons. One, to remind me about things that are important outside of medicine, right? Which is that there are things that are important to pursue outside of your professional career aspirations. But also, in that the 2 people that are in this picture with me are my father and my brother. This is a unique opportunity where all 3 of us got assigned to the same US Soccer Federation game, and we were the set of referees that refereed this. So for me, family is important, and this is a picture that resembles that for me. So taking the message of a referee, you may not agree with what I say here, and that is totally okay. And this is not a contact sport, so your water bottles and things on your table, keep them for you. But let's have some fun, okay? And you're stuck with me for the next 90 minutes. 20 minutes. So let's have some fun. Let's talk about creativity in surgery. I'm not going to go into surgical details. I'm not going to go talk about how to throw a certain stitch or how to do a certain procedure. That's not the goal here, right? You can find this on Google. You can find this on ChatGPT. I'm also not going to talk about nitty-gritties of the science. I'm not going to talk about laboratory protocols or specifics of how to do an experiment. Again, the purpose here is to keep it light and keep it interesting. But I'm going to give you the high hits of why this research is important and why this innovation that Susan introduced could potentially have an impact. What I want us to realize is that human disease is complex, and unless we ask impactful questions and design ways to discover answers to these questions, these are going to continue to be problems for us. And we have to be open to creative solutions and creative ways to be able to answer these questions. So, as Susan mentioned, I went to business school recently, and I went to business school mostly to learn hard sciences like accounting, finance, and analytics. But what I gained out of that program was actually more of the soft science, if you will. And one of the courses that we took in business school was on creativity. And I was thinking to myself, wow, what is this course going to teach me about creativity? And it was taught by Marcus Baer, who's the vice dean of the Olin Business School. And it was such an inspirational course. I came out of that course thinking to myself, wow, I am such a novice. There's so much to still be learned about the process of creativity. This is a whole discipline that you can spend basically dissertations on to understand how to develop a creative mindset and pursue creativity as a way to be able to enhance your productivity and ability to be able to translate new things. One of the things that Marcus emphasized in his coursework was challenging conventional wisdom is the tenet for creativity. You can't be willing to accept what is convention because that will muddy the waters. It will actually blind you from the possibilities that exist. And the other thing that he mentioned is that good ideas are out there for anyone to find. But the key thing is that you have to spend the time and the effort and work to find these solutions. Creativity is a process. It's iterative. It takes time to be able to achieve these things. So with that, I'm going to give you 5 thoughts about creativity and what I see its relevance is in surgery and in innovation. As I said, creativity, is it a light bulb? Is it a lightning? Is it something that flashes a moment of eureka? And most academicians would tell you that that's not the case. There are people that have built their academic careers on studying innovation and the process of innovation. Zorina Pringle at the Yale Center for Emotional Intelligence built a whole career looking at this and has published widely about creativity and what makes something creative and why is it recognized as something being creative. And she basically sums it off as, it's a hard process. There's nothing easy about this. It's exceptionally difficult to come up with new ideas that are fresh and impactful. And it needs a lot of exploration and a sense of commitment to it. It also requires a lot of goal setting and challenging convention again, thinking originally and developing the attitude that you need to be able to find something different. It takes commitment. It takes effort. Like most of us in our professional efforts, you have to be committed to this cause in order for it to be able to be fruition. If you look at these book titles, right? These are the people that we typically think of as innovators, creators, people that are totally thinking outside the box, right? From Elon Musk and thinking, how do we re-land a rocket, right? And the scientists that figured out CRISPR and Cas and how to do gene editing. The Apple CEO and founder, Steve Jobs, Einstein, Ben Franklin, and Leonardo da Vinci. All of these are individuals that we, attribute to being able to have creative minds and be able to develop really impactful new ways of thinking about things. And all of these things, there are common themes. All of them have challenged the process, and all of them pursued their interest as a labor of love. This was not just a moment's notice. This was not just a eureka moment for any of these inventors. These people took their labor as a sense of commitment, and it was something that they kept on doing and iterating and refining. There's also something that's common between all these titles. They're authored by one person, right? Walter Isaacson is a prolific author and is also the editor of Time magazine. Now, something is interesting about this author. He's not very social. You don't see a lot of media attention to him. He actually has a lot of creative anxiety. He admits this. He actually says that he labors over and over when he's creating these books, these biographies of these prominent individuals. And he always wonders, am I doing justice to these individuals when I'm talking about their creative works? And one of the things, again, that he says in his works is that in his over 60 books on biographies and different people of note, is that he puts in the hours. He puts in the work. He takes the grit and keeps on iterating and refining his work. And every publication or every book that he's done, he has spent countless hours trying to refine and improve and really do justice to the person or personality that he's talking about. Now notice, Walter Isaacson, despite his productivity, is yet to get a Pulitzer Prize, right? So even though he's been an incredibly prolific writer of this generation, at some point somebody will write a biography about him, He's yet to be recognized to the status of other writers of his generation. So one of the first thoughts that I wanted to share with you is that creativity is a process, and it requires a lot of effort. It's not something that happens overnight. It takes time, and it takes effort. But with that, I wanted to explore with you, well, what functions does a surgeon have that would allow them to be able to commit that time and commit that effort? Well, creators are typically ones that explore potential solutions. They look at option A, option B, option C, so on and so forth, and then they're able to screen them and see which ones work best. They take different perspectives, usually caucus multiple opinions, different people with different backgrounds, and gather diverse expertise. They sometimes recognize patterns, and in recognizing these patterns, they're able to see are common things being pursued by a certain population versus less common things being pursued, and perhaps the path that's less traveled is the one that they should pursue. And they're able to cooperate. Now, the individuals that we looked at a second ago, like Elon Musk and Steve Jobs, despite their personalities, they still were able to find the right talents, and they were able to collaborate with them in ways that are exceptional and very unique. They were able to find talents and find that talent and utilize it in the ways that allow it to flourish. Let's contrast that with surgeons, right? And see how many of these qualities, correlate with a surgeon. Surgeons are often, considering different curative solutions. In my field in vascular surgery, there's probably oftentimes 4 or 5 different ways that we can treat a patient with the same pathology. And the question is, which one do we feel is going to be best suited for this patient? For this personal patient right here, what do you do for this person to be able to help them overcome their challenge in a way that's least morbid but potentially has the best impact? You're able to assess the surgical risks and options of option A versus option B. And in discussions with patients, you can then decide which one is going to be able to have the best impact. Obviously, surgeons recognize patterns of disease. Pattern recognition in medicine is huge. And with surgical expertise and knowledge and years of experience, surgeons that have the most knowledge and expertise have a greater fund of pattern recognition. And surgeons, like many other medical specialists, need to know how to be able to work with nurses, trainees, and researchers from a broad variety of educational backgrounds in order to be effective at what they do. When you look at the job satisfaction of surgeons, look at the things that make it more challenging or make it fruitful for them. Among the things that are most challenging is not surprisingly, the things that are related to bureaucracy, right? In terms of reimbursement and documentation and electronic medical records. But the things that give satisfaction to surgeons is their ability to impact. Feeling that they've been able to do something that has a lasting impact on their patients. And this is important because when we look at job satisfaction in general, across all fields, not just medicine, you find that in 2018 and in 2022, pre and post-COVID, by the way, creativity is one of the highest things that people find to be impacting their job satisfaction. The more chance that they have to be creative at what they do, the more invested and interested they are in that job. Is that surprising? Not really, right? We would all agree that the more creative capacity that you have at what you do professionally, the more satisfied you're going to be with that job. This is important because particularly in the COVID pandemic, when there was a lot of stressors on our healthcare system, there were a lot of surgeons that were dissatisfied with their jobs. In fact, more than a quarter of surgeons that were less than the age of 60 were thinking about quitting, giving up surgery altogether, doing something entirely different than medicine. And if you look at the stressors, it's overall stress, work time demands, personal time requirements. You get a hint that it's all about values, right? It's not necessarily their patient interaction. They love that. It's about all the other competing values related to what they do on a day-to-day basis. And combine that with the surgeon that's an academic center, like Washington University and Barnes-Jewish Hospital, right? Someone that wants to be a creator, somebody that wants to innovate, somebody that wants to research new topics, they're faced by a lot of challenges from a funding standpoint. In order to be able to pursue an idea, you need funding, period. It becomes just an idea without the funding. And in terms of national grants and funding, they're on a continuous decline. And people that get the awards are usually later in their careers, well beyond their initial creative insights. It also provides limited salary support. So there are significant challenges from an economic standpoint to be able to support the academic surgeon that wants to be a creator or innovator. So in my mind, and something that I actually learned from Marcus Baer and my time at the Olin Business School, is that there are competing values that impact any professional in their profession, but particularly as a surgeon, they have competing values in empathy and care, their efficiency and productivity, their ability to be profitable for their organization in treating patients, but also a key component, in my opinion, is their ability to be able to innovate and create new things. And oftentimes, we correlate this with other organizations. Do other organizations have this? Of course they do. Robert Quinn is a social scientist and teaches at the business school in Indiana. He created this framework that actually many organizations use, not just in medicine, but in all kinds of organizations, particularly IT and software, organizations like Google. They use this to be able to define certain teams within their organization that need to collaborate, that need to be very hierarchical, that need to compete with one another, and also need to innovate. And their innovation groups are put into a category to allow them to be able to mingle and spend professional effort on ideas and creating new content. So let's implement that for surgeons, right? Let's create this context for surgeons. If we were to grade an academic surgeon on their empathy and care, efficiency and productivity, their profitability and capacity to be able to do surgery, and their ability to innovate and create. If it's a skewed balance, right, then their job satisfaction may not be that great. They may not be able to focus on the things that they care most about, and their values may be competing. But if it's much more balanced and have an equilibrium in all content, in all domains, both the care, the empathy, the profitability, as well as the innovation, there's a more balanced equilibrium that allows that individual to have much higher job satisfaction. Which brings me to my second point, that being a creator, an innovator, a creative individual will give you better job satisfaction. And to me, that has been the prominent area of interest for me, because that's been the area that's kept me going in my professional career. If we ask kind of the general public and other physicians and other healthcare professionals, what makes a good surgeon and what makes a bad surgeon? There's an overwhelming bias that a good surgeon is someone that has good hands, good dexterity, and good technique. And what makes a bad surgeon? Well, as we would expect, somebody that has not very good behavior. Either they're temperamental or they're arrogant or not very, very social, right? But if we go beyond this and we go beyond scratching the surface, you can look at the history of innovators in surgery. And again, I'm not going to give you a history lesson on this, but you only have to look at back some to see who has innovated in the field of surgery and had an impact. Someone like John Hunter, in the 1700s, approached surgery as a scientific method. So way back when surgery was still kind of in its early development phase, the scientific method was tenant to being able to develop different options for patients and pursue different hypotheses for what they think is going to work and what is not going to work. And as such, surgeons were now being able to change plans. So if the one course wasn't working, you can take a side road and choose an alternative. A If you look at other prominent surgeons across the fields of surgery, Joseph Lester took also that hypothesis-driven approach in instrument sterilization, figuring out that if he sterilized his instruments, his patients were less likely to develop gangrene and pus following their surgery. And that was a huge development in terms of being able to have an impact on his surgical technique as well as his patient lives. John Gibbons invented the heart and lung machine. This is an impactful discovery that's now, helped countless numbers of patients, right? But his process was arduous, and if you look at how he actually went about this, also it was a hypothesis-driven approach. Michael DeBakey invented Dacron grafts, among other things, including the artificial heart and valves. It was, again, an iterative process, hypothesis-driven, tested and retested and reapplied. And Patricia Bath, the first board-certified African-American ophthalmologist, developed a unique laser cataract surgery when she found that African-American patients in Harlem were more likely to become blind from cataract, and she wanted to be able to develop a way to be able to treat these patients effectively and efficiently. And so through her public policy and public health interests, she was motivated to develop a technique that would help her patients. But the heart-lung machine, what's interesting is that first prototype was 2,000 pounds, 2 tons, right? And it took over 20 years to be able to develop this prototype. And in a hypothesis-driven approach, John Gibbons and his team, using animal models, had to figure out why this circuit would continue to clot, develop fragmentation of the blood cells, foaming, air emboli, and out-of-control acid base, being that the blood is too acidic or too alkaline. And they could only solve these problems in a hypothesis-driven way. They had to develop new techniques, create new ways to be able to develop a prototype that they can actually then transition into a patient. Michael DeBakey. So Michael DeBakey grew up in a house that sewed clothes for a living. His mom was a seamstress. And when he was trying to treat aneurysms, he tried to find fabric that would not fatigue when he sewed it to the arteries. And he went to the fabric store, the local department store in Dallas, and asked for nylon. That's what he thought would work. Well, they were out of nylon that day. They had Dacron, this new material that nobody really was buying, and they weren't selling it. They asked him, do you want to try this? And he was like, sure, let's try it. And he sewed it into tube grafts, and guess what? We now have Dacron grafts as the convention, right, of treating aneurysms. How did he do this? He took a leap of faith and tried it and iterated on it, and sure enough, it worked. Again, lasophaky, which was invented by Patricia Bath. This is her patent application. You can see through a little tiny hole in the lens, they can go in and treat a full cataract. Before this, it was a morbid operation, and oftentimes it was an incomplete removal of the cataract. This is now the standard of care. How did they come up with this? It was an iterative process full of hypothesis-driven approaches. So the componential method for creativity only depends partly on expertise. And all the individuals that we just talked about, they obviously had to have a foundation of expertise. They were proficient at what they do, but there was something else, right? There was something else about each of these people that led them down the path of exploration, of finding a solution to the impactful problem that they were seeing. And it had to be something related to their intrinsic motivation to find a solution, right? Whether it's their public policy interest, the lack of care that they were seeing in certain populations, or their critical thinking skills. But there was something else that was related to the process of innovation and creativity. And it's only when you merge these areas of motivation, expertise, and critical thinking that this magic really happens. So the third thought is, it's not just expertise, right? We all can be creators and innovators in our fields. It depends also on intrinsic motivation and your willingness to critically analyze and pursue iteration. So if we take a step back and we think about, okay, well, if it's not just expertise, can a novice be an innovator? And I would say yes. In fact, the freshest and coolest ideas that I've seen are actually from people that are not experts in their domain, right? This idea of the new pink, it was not developed because I was an expert at islet biology, right? I'm a vascular surgeon, right? I don't work with islets. I don't work on pancreas. That's not my area of expertise. But I approached it from an area of vascular graft technology. As Susan was relating, I implant grafts in patients, but I wanted to reappropriate that fact that we sew the graft to an artery and we sew that graft to a vein in the setting of dialysis. And so the question is, why can't we use that as a potential organ? If it has arterial supply and has venous outflow, can we use that as a platform for transplantation? And this mindset was really ingrained in me by one of my mentors at Stanford, where Oliver was one of my vascular surgery attendings. He used to always ask us whenever we're wanting to study something, it's like, what is the big picture? Like, why are you really doing this? And what's the higher purpose of this? Let's start at the ground level of why this is important. And one of the things that Oliver and I did was that at the time there was a Google Glass software. I don't know if you guys remember that thing that Google had made. And so one thing that Oliver and I did when we were at Stanford is that we actually used it and reappropriated it in terms of being able to see vital signs and CT scans and imaging. And we actually published a clinical trial on this and started a company when I was a resident on the use of Google Glass. The problem obviously is that Google Glass went away. And so the company did not last. But it was a great introduction to the aspect of just thinking about the fundamental premise of innovation. And something that's unique about Stanford is that they have this biodesign that celebrates innovation, multidisciplinary teams, and they've done impactful things with this. Over 1 million patents, lots of inventions, tons of employment. And I found like-minded individuals that do this sort of stuff here at WashU and at Barnes. Eric Luthart from neurosurgery and Guy Jenin from mechanical engineering at the McKelvey School of Engineering have a tremendous output in this area of innovation and being able to work cross-disciplinary. And I said, I want that. I want to work with these guys. And so in collaboration with Guy Jenin and Eric Luthart, we've developed this model of synergy where you include medical experts, scientists, engineers, business individuals early on in this iterative process. And the idea is to prevent blind spots from happening early on during your creation. You want to be able to know what are the potential stumbling blocks as you're starting to develop this early on. And it synergizes quickly to be able to bring this technology to fruition a lot faster. And if it's not suited, you know about it earlier, right? Before you invest a lot of techniques in it. We co-founded the CVICE, which Susan introduced. This center is built on the multidisciplinary collaboration of multiple specialties in cardiovascular space. We have regular invention meetings. We call them that. They're called invention meetings, where we generate ideas, have executive triage, have a multidisciplinary approach to assessing them, and then we actually build these prototypes in-house, and then we test them. Again, it's an iterative process. And actually, Sophia, right there, is our first fellow in CVICE. So I just wanted to recognize her. So as part of this center, we have both surgeons and engineers involved. They have multiple projects that they both act as primary and secondary on, and they synergize with one another. And you can see the output has been tremendous. Multiple mentors, multiple publications, multiple patents, and the output has been marvelous. And this is the sort of thing and culture that we want to continue to be able to cultivate. So this brings me to the fourth idea here, in that fresh perspectives can catalyze innovation, and these perspectives don't have to be expert perspectives. They could be novice perspectives. In fact, we welcome that because I think it brings a fresh and new approach to these ideas. So I want to take you to the new PANC idea and tell you why the investment that Barnes-Jewish Foundation provided has been a tremendous catalyst to this idea and why it's going to give you a return on investment that's unbelievable. As you guys know, diabetes is a big deal, right? All of us know someone with diabetes. All of us, unfortunately, may have a loved one that develops this condition. And as we know, this condition doesn't necessarily have a good cure. Right now, it requires us to administer exogenous insulin, so insulin that is being injected into the body because either the body is not responding to the insulin that the host has or because there's a deficiency of that insulin. The body's unable to make adequate amounts of insulin. And the demographics are tremendous. This is going to continue to impact more and more people, and there's currently no cure. So what we've developed is a potential cure called the new PANC, which is basically a device that's attached to an artery on one side and a vein on another side. And spliced in the middle of that circuit is a treatment zone, which is an area where you can implant organs, cells, things that make insulin, right? And you can see that there's a porous membrane in that middle area, right? And that porous membrane is intended to allow real-time blood sensing of the blood glucose, so glucose can get into that area, and at the same time release insulin so that it gets into the host blood supply immediately without a lag. The porosity of that system also allows for nutrients, amino acids, any vital proteins to get to the cells to continue to nourish them so that they don't die away. And most importantly, it allows oxygenation, which is usually the biggest problem in implantation of these types of cells, is that they don't get enough oxygen. So this graft is able to then allow enough oxygen from the arterial supply to get to these cells to be able to keep them alive. So when we first presented this idea to collaborators, they thought it was crazy, right? They're like, yeah, that's not gonna work. And so we decided, okay, well, let's embark on making it ourselves. So we made this device homegrown in our research laboratory. This is the device that we created ourselves in our laboratory. Our engineers in the CVICE and in associated programs helped us put this together. You can see it's basically graft tubing, and in the middle of it, there's a spliced treatment zone, and then the cannulas that can allow us to implant things within this treatment zone. And ultimately, what we'd want to do is, in a patient, be able to implant it on one side to an artery and on another side to a vein, somewhere up here in the upper chest. And again, the way it works is that it allows for the easy diffusion of nutrients, keeping the cells alive within that treatment zone. We also had to figure out a way to be able to take cells from a human pancreas at Mid-America Transplant and be able to take it to our laboratory and be able to keep them alive while we put them into the graft. And so we developed a technology where we're able to take these islets or cells, protect them in a hydrogel, and then be able to then implant them into the device. And you can see these pictures, the green things, the green globs, these are the islets that make insulin, and you can see that they're protected with a hydrogel before we implant them into the device. And then we're able to take these devices and surgically implant them into a large animal host for testing before we transition it to humans. And I'm going to show you here some surgical pictures. I hope you're okay with that, but I think it would get the message across. And so you can see here that on the picture on the left, this is an incision in the neck of a large animal pig, so the size of a human being. And on one side, it's sewn to the carotid artery. On the other side, it's sewn to the jugular vein. So it's connected to an artery on one side and a vein to the other side. And you can see us here in this video implanting that treatment zone with the islets. So you can see there the fluid going in with the islets within the treatment zone. Notice also that graft is pulsating, right? It's got free blood flow within it. And these islets are sitting within that treatment zone, not coming in contact with any blood And so one of the amazing things about this device is that we don't have to give immunosuppression to the pig. We're putting human cells in a large animal pig with no immunosuppression, which is fascinating to us. The first time I got this result, I had to call my chief of surgery. I was like, guess what? We were able to put human cells in a pig without no immune rejection because we found a device that could be able to do that. Homegrown, done in our research laboratory in an iterative process. The most interesting thing, though, in addition to the no immunosuppression, is that we found that in these large animal pigs, we find that there's human insulin circulating in the pig's bloodstream. So what does that tell us? It tells us that these islets are not only alive, but they're also functional. They're making insulin and potentially showing us a glimpse of what's yet to come, an opportunity to be able to make insulin production de novo in a diabetic host, which again, to us, would be a home run. So we took our devices, we implanted them into these cute pigs, right? These Yorkshire pigs, these are standard farm animals, and Sophia's laughing because she knows what's coming up, right? And we decided, you know what? We're gonna implant them in diabetic pigs, right? Well, it turns out there are a host of diabetic pigs out there. They're very limited, right? But they're not so cute, right? These are Ossabaw pigs. They're a hog. It's really actually a hog. And if you look carefully, they actually have little tusks, right? You know, if you've ever seen The Lion King, right? This is Pumbaa, right? And so the Ossabaw hog can develop diabetes. And people in my laboratory, including Dahlia and Sophia and others, have been working hard to be able to manage these pigs that we implant with these grafts. And the data is actually very encouraging. I'm here showing you unpublished data, but this data wouldn't have been possible without your support. So this is a pig that we were actually going over data with today. This pig had the device implanted for 11 full weeks, right? So we kept this device in the pig for 11 full weeks, and you can see here, this is the explant. So now we're coming after 11 weeks to retrieve the device to see how does it look after 11 weeks. And you can see this device is still in there, still functional. When we take it apart and our engineers look at it, you can see the islets. If you can't see that, you know, it looks like little caviar beads sitting inside the graft in the treatment zone. And if we take these caviar beads and we look at them, sure enough, there are islets there that are still alive. 11 weeks post-op with no immunosuppression in these cute animals. And so what you can see here is our developmental timeline. And this, again, wouldn't have been possible without the resources and the support that we receive from you. And we hope and we want to continue this momentum to be able to advance this into our ultimate goal, which is a first-in-human phase 1 clinical trial. Obviously, this is going to take more work. It's going to take more iteration, more hypothesis-driven creation, right? Teamwork, but we're up for this challenge because we are committed to it, and we believe that this is going to help a lot of people. So my fifth thought about this is that high-risk but high-reward ideas can give big ROI, and that's what we're hopeful that we're going to be able to continue with this process. So I wanted to do some acknowledgments before I wrap up. So all of the work that I've shown you today would not be possible without these individuals. So these are the amazing, amazing people that I work with on a day-to-day basis in our research center. These are incredible scientists, technicians, researchers, postdocs, the people in the audience that work in our team. Please stand up. Please stand up. Don't be shy. Yeah, so I come up here and I represent our team, but they actually are the ones that do all this work, right? And you can't imagine how hard it is to do animal research. It is incredibly laborious, especially on wild animals. And so I feel very indebted to our team. This is an impactful book by Bill Campbell about the $1 trillion coach that helped multiple companies in the Silicon Valley become what they are now. And one of the things that is mentioned in this book is the importance of building the right team. And I've been incredibly fortunate to have the right team here, and without which none of this that I've shown you today and what we hope to accomplish would have been possible. I also want to mention my mentors. Eugene Oringer is the director of the MD PhD program at UNC Chapel Hill. He took a chance on me and let me into the UNC MD PhD program. And if he hadn't let me into that program, I don't know if I would be standing here. So just, for the program officers and program officials that have a control on the inlet of applicants, you have an impact on candidates' lives. And I think that's important to acknowledge. And if you look carefully, you can maybe see me here in the second row with hair, right? I also want to acknowledge my PhD mentor, Leslie Parisi, who's now dean at University of Vermont, but at the time when I was in her lab, she was the chair of the Department of Biochemistry, and a fantastic woman researcher, and she taught me important lessons not only about hypothesis-driven research, but instilled in me the fact that any data is valuable. Even when it's negative, there is value in that data. It doesn't have to be publishable data to be valuable data. Negative data is just as important and just as impactful as positive data. And that to me is a message that I carry on, and I hope that I actually carry forward to my trainees. I also want to acknowledge these fantastic doctors and physicians that have mentored me and supported me at what I do here as a faculty member at Washington University and Barnes Jewish Hospital. Clay Seminkovich is a chief of endocrinology here at Washington University. Fantastic physician and endocrinologist, and also researcher. And when I first started here at Washington University, I set up my lab as a bench in his lab. And I wanted to learn as much as I can about diabetes, even though it wasn't my area of expertise. And I still go to Clay's lab meetings because I continue to learn and be challenged every time I go to his lab meetings. And our researchers, including Dina, who's a postdoc in my lab, right? We have regular meetings with Clay to be able to get a fresh perspective from him on what we're doing and see if that is cutting the mustard. Louis Sanchez is the chief of vascular surgery, and Louis has been incredibly supportive from day one. He's given me the opportunity and the bandwidth to do what I do. He's the one that I called in the middle of the night about our islets working. He's like, okay, very good job, keep up the good work. And he's been an incredibly inspirational surgeon, extremely talented. When we talk about a creative surgeon, I see no one like Louis in the operating room. An incredible physician and extremely talented surgeon. And last but not least, I want to acknowledge Dr. Eberlein. I know he's sitting in the back and he's with us. Dr. Eberlein, as you know, he's a past chair of the Department of Surgery. Dr. Eberlein helped recruit me to the department, and without his support and his insight and his ability to recognize the importance of a surgeon scientist, again, I wouldn't have been able to be supported and be able to do the things that I do here today. So thank you, Dr. Eberlein, for letting me do what I do here every day. And to all my colleagues and friends that I have been able to interact with here at WashU. This is here at the OTM office, the Office of Technology Management. One of the things that's celebrated here at Washington University, unlike other places, is the entrepreneurial and innovative spirit. We were here celebrating the creation of Cayley Vascular, which is one of the companies that I started with these fantastic group of individuals. And this was celebrated. Our university and our programs here celebrate this. They want people to do this sort of stuff. And this is the fantastic thing about this climate, is that we're in an area that is supportive of these sorts of endeavors, which is truly inspirational and incredibly unique. And finally, I want to acknowledge our funding sources. So we've been very fortunate to get non-dilutive funding from the NIH, but it's foundations like Barnes-Jewish Foundation, the Scandalaris, Mid-America Transplant, that have been instrumental in terms of being able to allow us to be able to do this work. And so thank you again for your generous support and for everyone tonight for coming and joining us. But last but not least, I want to acknowledge my family. So my wife and my daughter are here. Our son is playing basketball. There's more important things, right? But I wanted to acknowledge my family because without their support and their willingness to put up with my interesting schedule, this also wouldn't be possible. And I love you guys, and thank you so much for all your willingness to support me. Any questions? And so there are microphones. We'll bring them to you, and then I'll pause a second after you say your questions so that people that are joining us virtually can hear you.
So I recognized in your presentation that you were working with Dr. Luthart, and I'm curious about the technology and how that relates to vascular issues in the brain.
Yeah, wonderful question. So Eric is a mentor. I treat Eric as a colleague, friend, but he's been an inspirational mentor. Eric Luthart, if you guys don't know or haven't heard about his work, it's truly inspirational. He's developed devices that can read your mind, literally read your mind, and be able to then allow for individuals who are disabled from a stroke or some sort of cerebral pathology to be able to control their limbs with their thoughts. And completely innovative work. And so when I came here to Washington University, I realized that Eric had a center, the CINT, or the Center for Innovative Neurotechnology. And I served as a co-mentor in this center to be able to collaborate with him and figure out solutions for neurovascular pathologies, right? And so these include cerebral vascular pathologies, these include anything that's in the extracranial carotid system. And amazingly, he and I came up with an interesting idea where we can retrieve blood clots using a modular approach. And so one of the companies that we started was Cayley Vascular with that intention to be able to try to design devices that can go through a little tiny puncture, smaller than a pinky tip, into a vessel, travel in that vessel all the way to the either cerebral or extracranial vascular structure, inflate 2 balloons so that you can encapsulate the area of the blood clot, and then remove it out. And so you can see from the fact that a neurosurgeon and a vascular surgeon and others collaborating, you can have tremendous capacity across multiple disciplines to treat a variety of pathology. And that's something I learned from Eric Luthart, and I wanted us to be able to implement this more broadly in the cardiovascular space. So he and I co-founded the CVICE, which now more broadly applies technology across cardiovascular disciplines within our Department of Surgery. And we're hopeful that further collaboration with Eric and others like him will be able to allow us to be able to bring more and more ideas to market.
Hi, my name is Nancy Koppler, and I am very poor in science, I will have to say, but I am very good as a mother and grandmother, and I do have a grandchild with type 1 diabetes. So I am trying to take all of this in. He's 14 years old, was diagnosed at age 8, and it has greatly inhibited his emotional development, I would like to say. He's very tall and he's a great athlete, but sometimes he's 14 and acts like he's 8. And I think some of it is his embarrassment. The first time he had one of the little, I can only think of the French word, a little truc, the thing that was attached to his side.
Yeah.
He was swimming, and his friend said, "What is that?" And he says, "I'm allergic to peanut butter." He did, and nobody understands, of course, what he's going through. But I am so excited about this. I was trying to take as many notes as I could. And in seeing this little device that you've developed, and I just feel like you're a god that you've been able to do this, and I'm so impressed this has happened in St. Louis, Missouri. I don't understand, and it's probably my lack of scientific knowledge, how do those little aisles get into the body? I mean, they don't have to find the pancreas, they just naturally tell the body how much insulin it needs at the right time, and then how do you reload it when you have to?
Oh, amazing questions, amazing questions. And,
Thank you.
And it's fantastic that you bring it back to your grandchild, right? And one of the things that we did with our recent funding is to reach out to individuals that have diabetes and try to hear from them what would they like to see in this device in order for them to find it usable, right? Would you want to use a device like this, and what would be the barriers for utilizing this sort of device as a cure, right? And one of the things that we repeatedly heard is peace of mind, right? Just having peace of mind that I don't have to check my blood glucose, and I don't have to worry about the highs and the lows, particularly the lows, right? And for everybody in the audience, it's not the high blood glucose that typically can be catastrophic for a type 1 diabetic. It's actually the lows, right? It's overdosing on the insulin that becomes a problem. And so having an implantable device that's implanted into the body, the blood glucose is circulating continuously. It has either high amounts of glucose or low amounts of glucose. In the setting of type 1 diabetes, without insulin being in the body, you're going to tend to have higher glucose, right? And without the body being equipped to be able to sense that blood glucose with the islets that make insulin, that's the body's natural factory for insulin, you end up having unchecked blood glucose with no production of insulin. This device would be able to take that advantage of that by being spliced in the arterial system. Sensing the blood glucose would happen in real time. It wouldn't be checking the subcutaneous, for example, interstitial fluid that is, with the continuous blood glucose monitors. This is actually sensing the bloodstream's glucose in real time. And as such, the islets that are in the device, that are housed and staying in the device, release the insulin immediately upon sensing the high blood glucose into the bloodstream so that it's active right away. And that's where insulin needs to be. It needs to be in the bloodstream in order for it to get to the organs that it then affects. So the whole idea is being able to have real-time blood glucose sensing, but also at the same time have real-time insulin production so that it impacts the body's ability to respond. So my hope is that for individuals like your grandson, is that one day we would have a way to be able to implant a device like this in them, and be able to allow them the peace of mind they don't have to check their blood glucose and don't have to administer insulin. This device would be designed hopefully in a way where we could replenish these cells if we wanted to. And I haven't shown you some of our new prototype plans, but basically they would be equipped with a valve that you can inject transcutaneously through the skin and replenish these grafts with cells that would be able to then allow to function in vivo again. Thank you for the question.
Thank you, Doctor. First of all, I'm a parent and a grandparent, and I think we should all say a prayer for Dr. Zayed, whose son is, his second day of his driver's license. So,
That's right.
been there, done that. Good luck. I'm really interested in the combination of the engineering team from Washington University combining. When did that process start, and how long has it taken to get to this point with the device you have now? And are there new materials involved in that? Are they using handy tools you had around the house, or is it something new and unique used in this thing?
Yeah.
And I also, and we have some diabetes in the family as well, particularly my daughter-in-law, I'm concerned. And is there a group that participates in this are you looking for people to work with? How would somebody get involved to share their insights and information and concerns?
Absolutely. Wonderful questions. So I'll take the first question first, which is, how long has this process been going on? So as you can see from this timeline, it's started in 2019, and it started actually when I was attending a symposium. Biomedical engineer was talking about the use of stem cells, so pluripotent stem cells, and trying to differentiate them into islets. So they're taking a stem cell and then trying to kind of maneuver it to become an islet that develops insulin. And one of the challenges that they were having is that, sure, they can get it into an islet, but they were having a challenge getting it implanted in a host. How do we get it into a large host? And so we started thinking together, well, is there a device that we can make that could probably house this islet so that then it could function and meet the needs of the patient, real-time blood glucose sensing, release of the insulin in real time. And that's how we came up with this potential idea of using a graft that's spliced with a treatment zone. And as you can see, it's been an iterative process. There's been multiple kind of benchtop assessments, prototypes that we've been developing, different awards that have been helping us along, little small investments here and there that have been inching us forward. In terms of the biomaterials that we use, remarkably, these are off-the-shelf biomaterials that we buy pretty cheap off the open marketplace. It's just how you put them together and how you configure them that's entirely novel and unique. So for example, the outer tubing, that's PVC tubing, right? That's stuff that you can buy from a hardware store, right? But the inner lining, the porous material, that's a porous PTFE material that is unique and has a certain pore diameter that allows insulin, glucose, amino acids, glucose and insulin to pass through, but not cells, not immune cells. And that's probably the form factor here, right? This is kind of the unique thing about this design, is that it acts like a blood-brain barrier, right? It prevents certain cellular types from getting in, but allows nutrition to pass through and the insulin to pass through. And we anticipate, by the way, that this is going to continue to progress, right? The biomaterials and the manufacturing of this has to be scaled in a way that's going to be useful for a go-to-market strategy, right? What we're dealing with here in the lab is not necessarily going to be what the FDA wants to see in a patient, right? And so that process will continue to iterate, and we'll be able to find a solution for it with the right team in place. But the energy and the interest and the capacity to do so is there. We'll be able to figure out these needs as we continue to progress this project. And as you can see, we're already aiming for mechanisms of funding that can help support this endeavor. And in terms of the patient population, we are always open to talking with patients, right? This is something that I find is part of that synergy model early on. The voice of the patient is a critical piece of that solution, right? You need to hear the patient's opinion early on. I was recently at a vascular symposium, and Jim was at this vascular symposium. It was at San Francisco, hosted by the Vascular Cures Foundation. And what was amazing about that foundation is that they had patients in the audience and in the think tanks involved from day one. And I think that is important to involve the patients early on so that the scientists and the researchers and the physicians are taking that into account from the beginning. And the type of patient that we would hope to implant this in as a first go-to-market strategy would be a patient that is failing at their insulin regimen currently, right? And unfortunately, there are patients like that, whether it be that they're just not able to control their highs and lows, or because they're having organ damage related to their diabetes. These are the patients that are in need of this technology, and these would be the first patients to receive it.
Thank you, Dr. Zayed. We're going to take 2 more questions until we continue into the reception and closing remarks.
Hey, Dr. Zayed, excellent presentation, incredibly thought-provoking. I have the main question, and I know you mentioned this, but I want to go back to the point that you said that you did not need immunosuppressants for your pigs in order for them to have the device implanted and still functional. So my question is, this means that you basically were able to create a blood treatment zone barrier of some sorts. Are you planning on using this technology elsewhere in other areas, or do you have any plans for that? Because that's really interesting.
Yeah, that's a great question. So you're right. The true value of something like this is not just going to be limited potentially to treating diabetes, right? If you have a particular cell type that manufactures or produces a particular hormone of interest or peptide of interest or gene of interest, and you don't want it to be rejected by the host's immune response, this could potentially be a platform of example, right? And when we come, for example, when we came to patent this, right, and file our patent disclosure, Washington University was very, very keen in terms of making it as broad as possible, right, and saying it's all encompassing for potential disease pathologies. So yes, so you could think of this as potentially a conduit for thyroid cells, parathyroid cells, adrenal cells, cells that are treating potentially gene therapy, or even as a drug-eluting platform. Instead of going to a chemotherapy center 2 to 3 times a week, perhaps having that drug instilled in that device and letting it elute for a period of time. So there's multiple potential cellular as well as drug delivery options for a device like this in the future.
Yeah, thank you very much for a very interesting talk. It's amazing what you've done so far. My name is Steve Rudinsky, and I bring cutting-edge scientists for many years from Simon and Barnes to speak at OSHA Lifelong Learning. Recently, I brought a Dr. Jeffrey Millman to speak at OSHA, and he's done some remarkable work taking skin cells to make them into islet cells, and he has reversed diabetes in mice. As I sat here listening to you, could we take his techniques and make these islet cells and put them into your device? It would seem like we have a ready-made way of getting these islet cells into your device, and that would be a great way to reverse diabetes in humans. And I just didn't know if you knew about Jeffrey Millman, and maybe you two could collaborate and work, and we could have a revolution here.
Absolutely, absolutely. Actually, Jeff and I go way back. So the biomedical engineer that I talked about at the symposium, that's Jeff. So it was him that I was talking to about the stem cell and the differentiation of it and getting it into an islet. And guess what? Our first experiments that we did were actually using Jeff's stem cells. So down here we depict these stem cells. So we actually can take stem cells and we can actually differentiate them into beta cells, and we can actually put them into that device. And guess what? We can implant them in the pig and have also a response, which is amazing, right? And again, these these stem cells don't require immune suppression still. There's one difference though. There's one key difference between using a stem cell that's differentiated into a beta cell and a whole islet that you can get from a living organism. And that the islets have multiple cell types. They don't have just insulin-producing cells. They also have glucagon-secreting cells. They also have somatostatin-releasing cells. These are other hormones that are important also for the glucose metabolism in a person that has type 1 diabetes. And so not only are you providing them the insulin which they need, but you're also providing them the whole organ function, which is just as critical, right? In terms of managing, again, the highs and the lows. And one thing I want to bring your attention to, if we can put a human islet in a pig, can we do the opposite? Can we take an animal islet and put it in a human? And at that point, you've negated the problem of limited organ supply. And that really could be a potential revolution.
Thank you, Dr. Zayed, for the outstanding presentation. Now I'd like to welcome Tom Cohn to the stage for closing remarks.
just in case they don't screw up. Thank you, Dr. Zayed. And congratulations on such inspiring and life-changing work. I was expecting to learn a lot tonight, but I was not expecting to be inspired on multiple levels. I think probably everybody here was in one way or another. It's been enlightening to hear about Dr. Zayed's research, discoveries, and innovations. We look forward to hearing much more about the evolution of NUPANC. As mentioned, I'm Tom Cohn. I'm a board member of the Foundation for Barnes-Jewish Hospital. Since joining the board nearly 5 years ago, I've gotten to see such impressive progress up close and personal. The impact you, our donors, are making in partnership with the foundation continues to grow, and it's very exciting to be part of. Our donors are behind so many advances in healthcare today, and we're truly grateful to you. We hope you're equally proud of the progress you make possible, and hopefully you see the impact you're having. Thank you to the foundation for hosting this enlightening event tonight, and thank you for joining us. We hope you enjoyed Dr. Zayed's fascinating presentation, and we look forward to seeing you at future leading-edge medicine events presented by the Foundation for Barnes-Jewish Hospital. Please consider sharing what you've learned tonight with your friends and family. You can also share the video of this program, which will be posted on the Foundation's website and social media channels. And now, please stay a little longer, enjoy more hors d'oeuvres, cocktails, and conversation with friends and colleagues. You also have an opportunity to mingle with Dr. Zayed and ask any additional questions. Thank you for coming, and have a wonderful night.